Dear colleagues, best wishes for the new year. I will speak today about phase transitions for Gödel incompleteness. This talk will be a talk about mathematics, but for non-mathematicians. So mathematics is usually based on what we say is set theory. And you all know from school what set theory is about, but maybe not what set theory does about the infinite sets. And that's what I'm speaking about. Infinite set theory speaks about cardinalities and ordinals. And to start, let us consider an example for cardinalities. Consider the plane. Here is 0, here is 1, here is 1. And then one can ask the question, how many points are on the unit line? And how do they compare with the unit square? So the question is, are there more points in the unit square compared with the points on the unit line? And the first basic result in set theory is no, these two sets have the same number of elements. It's completely counterintuitive. And this distinguishes naive set theory from university set theory. That's already some non-trivial exercise. The next thing which I want to explain are the so-called ordinals. Ordinals are about counting. So they are used for counting. So we start with 0, 1, 2, 3. And we continue. We all know what the natural numbers are. But in infinite set theory, one doesn't stop after the natural numbers. One introduces a first limit element. And then one continues counting, so let's consider the successor of the first infinite object, the successor of this number, and we get a second copy of the natural numbers, and there's no reason to stop. We can even count to the second limit. And by iterating this, the n many steps, we get the nth limit. Now there's no reason to stop. We continue further and we get the first limit of limit points, which is omega times omega. But there's no reason to stop. We can continue further. Omega times omega times omega. And after long enough counting, we get omega to the n, which is the first limit of limit and then n times iterated. So this is already a big number. But of course, there's no reason to stop. We can consider the limit of this counting. Well, as I said, we are going about infinite sets. There's no reason to stop here. So we can continue into the transfinite. So we get omega to the omega to the 2, omega to the omega to the 3, omega to the omega to the n. And another big ordinal, namely omega to the omega to the omega. And there's no reason to stop over here. We can continue even infinite iteration over here. This gives a number called epsilon 0, and we can continue further and further. And as I said, there's no need to stop. These are very nice objects. What can we do with them? Well, we can show that we can generate every mathematical object just out of these numbers. How can we do this? Well, we build a formation, a hierarchy. At the bottom level, we start with the empty set. And now we generate out of the empty set every mathematical object. How does this work? Well, we use these numbers and define a process by iteration using the power set. The power set, well, we assume that we have given a previously defined set V alpha, and then we consider the power set of it, forming a new set. And then we do this for all those numbers over here, and if you get the limit element, we just take the union of the previously defined objects. And then we can show for every mathematical object, for every x, there is an ordinal alpha such that x is in V alpha. Well, that's nice. What does this mean? This means the whole of mathematics takes place in a universe like a V-shaped universe, where in the middle you have the line of ordinals. And if you have reached height alpha, then you have the alpha stage of this hierarchy, and you can stratify all mathematical objects into such a picture. That's Cantor's paradise. Now, forming sets is dangerous. Well, what do I mean by this? There's some danger involved. And the danger is as follows. Well, take a property phi describing sets. Then set theory speaks about forming new sets, namely building collections of sets X fulfilling property phi of X. And comprehension says if you have a property phi, then we can form the set Y consisting of those X which satisfy phi of X. People have worked for a long time with this definition, but now in 1908, Russell found an example. He wrote down the formula phi of X is equal to the formula X is not an element of X. Now plug this formula into this definition, then you can check that Y is an element of Y. If Y fulfills this formula, if Y is not an element of Y, and if Y is not an element of Y, then Y fulfills this formula, then Y is an element of Y. But this is not possible. An assertion A cannot hold simultaneously with this negation. So what does this mean? This means forming sets needs a certain care. The way out was replacing comprehension by separation. It's possible, given a set A, to form the set of X in A using property phi of X. That has been suggested afterwards as a replacement for this dangerous axiom. Now the question is, how can we be sure that this operation of forming sets is still okay? Could it be possible that something like this could happen also for this type of definition? And indeed, there's no obvious reason why problems shouldn't show up in the new situation. For this reason, some mathematicians said we don't want to have this one, we want to have a rather sure foundation. And they wanted to base mathematics on predicativity. Namely, in forming sets, you're only allowed to use sets which you already know to exist. And such properties phi here could speak about objects which are not already existing. Another area of mathematics was intuitionism. And it was also considered as a program to get rid of these foundational issues. Now, the most influential mathematician of that time said, this is going much too far. Hilbert said, we want to stay in Cantor's paradise, but we also want to have sure foundations, a safe foundation. So we want to stay in Cantor's paradise. For this purpose, he invented a program, the so-called Hilbert's program. And this program consisted of two parts. First of all, he wanted to formalize mathematics, so develop a frame for all mathematics which exists. And second, once you have formalized everything, you can investigate your formalism by mathematical means. And then show consistency of mathematics by finitary means. What does this mean? You should show that there's no contradiction in mathematics using only methods which are safe. Well, of course, if your meta theory is not safe, then you can prove everything. Now, what could be a formalization of finitary means? Mathematicians have, of course, a long tradition, and they know for sure what the natural numbers are. So natural numbers are basic objects, and if you want to reason about proofs, we should know what the natural numbers are. This is a basic set consisting of finite objects. Natural numbers come, well, you have 0 and 1, and then by adding a 1, you can obtain every natural number after a finite amount of time. You have natural operations on natural numbers, namely addition and multiplication. Now, using the natural numbers, you can try to set up a system describing the natural numbers. The system is called Peano arithmetic. And what is about Peano arithmetic is about the natural numbers. So we have axioms for the addition. X plus 0 is x. X plus the successor of y is the successor of x plus y. X times 0 is 0, and x times the successor of y is x times y plus x. Now these are the basic rules for addition and multiplication, and you can prove a lot with these equations. Once you have a proof principle which is called induction. Now what is mathematical induction? It's the following proof principle. If we have property A, namely that for formula phi, speaking about natural numbers, we have that phi is true for number 0. And B, assuming that phi of n is true for natural number, then this, if you can show that this implies phi n plus 1 is true for phi. If this holds for all numbers n, then you can conclude phi of n holds for all numbers n in n. And these are two basic principles for the natural numbers. You have basic rules for the operations, and you have one proof principle how you can conclude statements phi of n for all numbers n. And now the Peano arithmetic is a system which can be identified with given arguments infinitary means. So proof in pure arithmetic is something which you can consider as a safe argument. Now what Hilbert would like to have is pure arithmetic should formalize a large amount of mathematics. So if the wishes were A, if phi is true, then phi is provable from the axioms of the pure arithmetic. And B, well, I don't go into the details, but pure arithmetic is very strong. You can somehow describe argumentations on proof figures in the system. So you can write down a statement that PA does not prove that 0 is equal to 1. And this can be written down as a statement about natural numbers. And then you can ask whether finitary mathematics can prove that the system itself doesn't prove a contradiction. And Hilbert's program, in some sense, would consist in proving A and B. Now, people in mathematics wanted to verify this, but in 1931, Kurt Gödel showed first of all, assertion A is wrong. So what does this mean? There will be statements phi which are true, but not provable from those axioms. And B, assertion B is wrong too. So PA is a nice system. You can speak about provability in PA, but you can prove that you cannot prove in PA that PA is free of contradictions. And that's a shock somehow for Hilbert's program, and somehow came to a stop. So it's not possible to prove that mathematics is free of contradictions by using finitary means. Now one could be interested in figuring out what is the nature of such sentences. What are examples for statements phi which are true but not provable? And many mathematicians may have never heard about this phenomenon, and the explanation is that the Gödel sentence phi is somehow cooked up. It is referring to the probability in PA, but it's just an assertion about logic, but not so much about mathematics. And this changed drastically in the 80s. So around 1980, Jeff Paris and Harvey Friedman showed that there are also mathematically interesting statements phi which are true but not provable. And I would like to speak about the contribution of Harvey Friedman. So Harvey Friedman has found a nice statement about finite trees. So the question is, what is a finite tree? For this purpose, I brought along two pictures. Here's one finite tree. Here's another finite tree. And those are from my Facebook page. So I painted them by myself. So the question is, what is a finite tree? A finite tree looks like this, right? That's a finite tree in our notation. Now we have to put it into a mathematical definition. So for this purpose, a finite tree is what? A finite tree is a poset, a partially ordered set. So what's a poset? A poset consists of a set X. What's a set X? That's a set of nodes over here. And it comes together with a binary relation, less than or equal to on X, which is a partial order, such that we have every node is less than or equal to itself. Well, what's the ordering relation? The ordering relation between two nodes is a top X sits above a top Y. If there's a line going from the upper node to the lower node. Well, X is less than or equal to X. Every node is less than or equal to itself. If X sits below Y and Y sits below Z, then of course X sits below Z. Just have a look. Well, if X sits below this node and this node sits below this node, then this node sits below this node. And if X is below Y and Y is below X, then X and Y are equal. That's also fine. And a poset is called totally ordered if two elements are comparable. If it is a tree, total order, no. Just consider those two nodes. They are not comparable. And that's a poset. So every tree is a poset, but not every poset is a tree. A tree, a finite tree. Maybe I should go to so a finite tree is a finite poset T with the less than or equal to relation such that, well, what do we recognize? If you look at this picture, there's a root, a minimal element. There is a root. And secondly, if we take a node in the tree and look down to the root, then we see on this way down, every two nodes are comparable. So B, if T is in T, then the set of predecessors is totally ordered. And that's a finite tree. Now, if you consider a finite tree, you can see that two nodes have a greatest lower bound. If you take two nodes and we go down to the root, there's the first point where those two ways meet, and that's the greatest lower bound. So for a tree T, if you have two nodes, then there exists infima for two nodes T and T. And I say one tree is contained in another tree if there is a mapping respecting the tree embeddability, the tree relation. So this tree here looks less complicated than this tree over here. So the red tree should be embeddable into the more complicated tree. How can we turn this into a definition? We say tree T is embeddable into tree T prime if there is a one-to-one mapping mapping different nodes to different nodes. It says a 1-to-1 map H from T to T prime, such that H preserves infima. So if you have an infimum in T, then it's mapped to an infimum in T prime. Okay, that's the notion of tree embeddability. What can we do with this? We can write down statements. And Harvey Friedman wrote down the following statement. Friedman's finite form of Kruskal theorem is the following assertion. For all numbers k, there is a number m. K and m are natural numbers, so big such that for all sequences of finite trees of length m plus 1, which satisfy a certain condition, such that the number of nodes in the ith tree is bounded by k plus I, if this such that if this property holds for all I less than equal to m. What does this say? This sequence of finite trees is not completely arbitrary, but it is controlled by a linear growth rate. The ith tree, the number is bounded by this k plus the number I. So if the sequence of trees is not too chaotic, then there are numbers I and j less than equal to m, such that I is less than j and the ith tree is embeddable into the jth tree. That's an assertion about finite combinatorics. It involves just finite trees, the tree embeddability relation. And you may ask, is this statement true? And indeed, FFF is true. But it's not easy to prove this. Because the arithmetic is not able to show this statement. So this assertion here is a statement about finite objects, which is so complicated that the usual axioms about natural numbers don't show it. That's part one of the talk. It's about Gödel incompleteness, but I'm speaking about phase transitions. Where is there a phase transition for this result? Well, if you remember from physics, a phase transition looks like this. You have, let's say, the transition from ice to, let's say, water. And if you consider the temperature, around 0 degrees, something happens, namely ice changes to water. So if you want to have a phase transition for Gödel incompleteness, we need something like the temperature, something which you can vary, such that there is some movement going on. And what we can do is we parameterize the assertion by Friedman by using a number theoretic function f from natural numbers to natural numbers. For this purpose, I consider a parameterized version, Friedman's finite form for function f. And for this purpose, I replaced k plus I by k plus f of I. Then f for the identity function is true but not proven. Now just imagine that you replace this identity function over here by a constant function. What happens? Well, then this statement is true for simple counting reasons. If f is a constant function, then you just need an upper bound for the number of trees having a bounded number of nodes. And this is an exponential function, and PA is able to speak about exponential functions, to prove properties about it. So PA proves f of f for constant functions. Now, what does this lead to? To the following transition diagram. If you have functions growing quicker than the identity function, we have unprovability, and for constant functions, we are in the realm of probability. And the basic question is there something natural in between, where there's a threshold, where there's a jump from probability to unprobability? In 1985, Matuszek and Löbel showed the following result. Namely, consider the function fr of I, which is r times binary log of I. And the assertions are A, if r is less than or equal to 0.5, then Friedman's assertion becomes provable. And B, if r is bigger than 4, then PA does not prove this assertion. So what we see over here is a picture like this. We have here the number system. Here is 0. Here's number 4. Here's 2. 1, 3. If you are above 4, with this R, then we have unprobability. And if we are below 0.5, then we have probability. Now, somewhere in between, there will be a jump. No one could guess where the number is. The number is about here. So the result is let C be a number. It's 0.6395578175. That's the number. And A, if R is less than or equal to C, then PA does prove the statement. And than C, then it does not. Now you can ask, what is this number, right? Is this related to pi or the Euler number E or the Euler number gamma? And it is not known. The nature of this number is not yet clarified. But there's a description of this number. So what is the description? Now something unexpected will happen. Namely, we consider complex analysis. T of z is a power series. Having certain properties, namely it fulfills a functional equation of the form T of z is z times exponential of sum over the t z to the I divided by I. I goes from 1 to infinity. Now this is not a recursive definition, but I am claiming that there exists a solution for this functional equation with a property let rho be the radius of convergence of T. Then we can show that there exists a solution having a radius of convergence bigger than 0. And actually you can calculate this row using this implicit description using Maple and define C as -1 divided by binary log of row. And this is the number C showing up in the theorem. So rather unexpected, by looking into analysis, we have been able to find a number of relevance to the Gödel theorem. This is the end of the story. Not really. So the next step is I consider a function f epsilon, where epsilon of I is a function going to 0. And if epsilon of I is what? Is C plus epsilon of I times the binary log of I. Now what is the point with this function? It somehow hits the area between numbers bigger than C and C. And now the aim is to classify the phase transition in terms of the speed of epsilon converging to 0. Is this possible? Well, I was working on this for a long time, and in fact this is possible. And how does this go? Well, it's also very surprising. So we are producing big numbers. What is a big number? f0 of x is 2 to the x, the exponential function that produces big natural numbers. Now f1 of x is I take f0 of x and I iterate f0 of x quite often, namely x plus 1 many times. So what does this give? This is an iterated exponential of height x plus 1. That's a rather quickly growing function. f2 of x is an iterate of f1 of x. f3 is an iterate of f2. In general, f alpha plus 1 of x is the iterate of f alpha, iterating this x plus 1 many times. So if you jump through the natural numbers, you already get a function producing big values. But we don't stop here. We go to the transfinite. We take f lambda of x is the maximum sort diagonal function of the f beta of x, where beta is less than lambda, and the term complexity of lambda is bounded by x. So these functions f alpha become quicker and quicker growing when the ordinal index increases. Now I take the function inverse of such functions. What is going on here? The f alpha functions are quickly growing. Function inverses are extremely slow growing. So the function inverse operates like this. It's the smallest m such that f alpha of m majorizes I. So if you implement this on a computer, you will never recognize that there is any growth of this function involved. Maybe it's a constant function bounded by 10 whatsoever, but in theory this converges to infinity. So this goes slowly to infinity. And then one can show PA does not prove FFFF for the function f, and epsilon is 1 divided by h epsilon 0 inverse of I, where epsilon 0 was one of the ordinals which I showed on the board. And if one goes a bit below, it becomes proofing. So that's more or less a complete picture of the phase transition regarding Friedmann's theorem. Now, have you seen big numbers today? The answer is yes. Well, take your favorite number 42. And if you want to produce a big number, take this number. This number is so big, it's of course bigger than the number of atoms in the universe, but it's much, much bigger. There's no way to describe this number by means of functions which you have ever seen. But there's a number on the board which is even bigger than this number. And it's a number coming from this statement. Namely, you fix the identity function here, and you plug in for k 42. And then you check what is the smallest possible m, such that you find always such numbers I and j. And if you take f of for the identity function regarding k equal to 42, this number will be much, much bigger than this number. And it's even much, much bigger than whatever you can think about. You can iterate these numbers as much as you want. It will always be smaller than this number. This number can only be described using this formulation. And it will be very difficult to find an alternative process defining bigger numbers. So that's the mathematical part of my talk. For our research group, we are working on such phenomena. We want to single out mathematically relevant applications, nice examples where these phenomena show up. And it's the interplay between logic and analysis, like the complex analytic function I showed before, which is used in this business. And for large amount, we base our research on a book by Philippe Lajolet, Analytic Combinatorics, which is quite basic for the analytic part. Thank you very much.
Thank you very much, Andreas. You have given us a nice little peek into the minds of some very bright people. Is anyone daring to ask a bright question? Yes, Connie van Straten.
Does your function grow faster than this Ackermann function? I know that.
Yes, yes.
This is even growing faster.
Much, much faster. The Ackermann function shows up at level omega, the first limit. But if we are going much beyond the Ackermann function. So whatever you do with the Ackermann function, you will never be able to reach this number. You can take the Ackermann function, plug in the Ackermann function as an argument, again, whatever you do.
Any more inquisitory questions? Yes, van der Jeugd.
Maybe just one mystery in a way. You say that, for example, this property at FF, you said at one point, we can prove it is true, but then it is not provable.
Right. So one has two things, provability from the Peano axioms, and of course there's all the provability in set theory. So in set theory you can prove that this is a true theorem, but the Peano axioms are too weak to prove this. So you have to go beyond the Peano axioms.
So it depends on the system that you work in to prove something, whether it is...
Yes, yeah. And Harvey-Friedman even showed results for set theory. This is even much more complicated.
Okay, one last question. If not, yes, please, Colin.
So where does the axiom of choice kind of come into that?
The axiom of choice does not play a role for Peano arithmetic. So it's an axiom of set theory. And actually, the funny thing is, if you can prove arithmetical assertions using the axiom of choice, there's a meta-theorem showing that you can even do it without the axiom of choice. So the axiom of choice doesn't affect such theorems.
Okay, well, thank you very much. I thank our speaker again. Thank you very much. See you.